Again, a very warm welcome to the webinar Ceramic 3D Printing, Advancing New Applications in Additive Manufacturing. My name is Johannes Homa. I am a co-founder and CEO of Lithoz. And I also will now introduce Davide Sher, is CEO and founder of 3D PPM, which is an online magazine on 3D printing. I'll try to explain a little bit about him. So he's the founder of 3D PPM. He's doing a lot of market research, marketing, and media agency for 3D printing industry. They have two things which they are publishing. That's the 3D Printing Media Network and the 3D Printing Business Directory. Davide is also analyst for SmartTech. I don't know if you know them, but you will see some details in the next couple of slides. And they are doing market research on additive manufacturing and as well on ceramic and this current state of the art market research with market scenarios and forecasted adaptation till 2030. The full study, of course, is available if you want to download it for some money input. But Davide can tell you a little bit more here as well. Since Davide is still has some issues. But anyway, I think a couple of things I want to mention here is that we see, the ceramic additive manufacturing market is, so to say, the youngest markets beside metals and plastics, and but is expected to have, of course, a similar growth, but of course a little bit later than metals and plastics. But as always, the market is very much driven here, much more than with the other two markets. It's driven very much by technical applications. So these high-end applications are going to drive the market and the hardware. And you will see afterwards in the presentation. Ceramics is a very unique material, and we are working in high-end applications only. So therefore, it's important that we are looking also into high quality. And I think it will also drive the sales for technical ceramics materials. And what Davide is presenting here, you see that the total revenue associated with ceramics additive manufacturing. So we have technical applications. Davide?
Hello, I'm so sorry. You exactly when this started, the biggest thunderstorm I have ever seen just exploded. just went off at the same exact time as the meeting started. I apologize. For the delay.
Things like this happen. Davide, I took over so far, and I introduced yourself, and are already here on the first slide.
Thank you. I apologize, but this is like Murphy's Law to the extreme. I've never seen anything like this.
No problem. You can take over from here now. Good to have you back.
Thank you very much. Thank you very much. Thank you everyone for being here. Sorry for the accident, for the incident. So let me just jump right into this really quickly. We're going to be talking about advanced ceramics applications with Lithoz. Is one of the market leaders in this segment. Very fascinating company, amazing technology. And I just want to set the stage a little bit to describe the market, because what I do is basically I report on everything that happens in the additive manufacturing market. I try to see what's happening. I try to make forecasts on the future. And we published a report not too long ago on ceramics additive manufacturing. And the basic, I'll be really quick. I don't want to bore you too much with data, but the basic point here is that the market, we do expect the market to be to become a significant business opportunity with over 4 billion in revenues, but driven by advanced ceramic applications. And as you can see here in the chart, it's a bit of a of a hockey stick chart with rapid growth in the upcoming few years. And we actually when we started tracking the market, it was almost non-existent. And what happened, and what we're seeing, and so we made our forecast, and we thought they were even too high. But what we're seeing is that it's actually happening. I mean, there's such a great potential for advanced ceramic 3D printing applications that the market is going to be growing really quickly. And ever since we started tracking the market, it's now moving into production, and so the numbers are growing exponentially. This, of course, will drive the sale of hardware and materials. Okay, I have. Okay. Here. Okay, I'm at the beginning. Let me just go to the next. So, who are the users of ceramic additive manufacturing? We've identified three types of companies. One is the industrial adopters. So the companies that make ceramic parts, or actually not even the companies that make systems, and they use ceramic part for those systems, and they're going to eventually be bringing a lot of the production, internalize the production through the use of additive manufacturing. This is more long-term. More immediate, we see ceramic industry companies, so material companies that they sell ceramic materials, but by investing into ceramic 3D printing, they are able to sell parts, not just materials. So and that creates a lot of added value, because if you sell a printed part, it has a much, much higher value than the materials themselves. The third type of companies is AM industry operators. So specialized 3D printing companies and 3D printing hardware manufacturers that start offering 3D printing service using ceramics to the industry. The final slide I wanted to show you is the application. So where are these technical ceramic applications going to be used? The key segments that we've identified are aerospace, biomedical, electronics, and the dental segment. These are the first segment. These are more short-term opportunities. These are segments where part cost is not as relevant as others. They have lower production volume requirements. More long-term opportunities we see are in the automotive and energy segments. These are segments that make automotive. They make a lot more parts. They need to make a lot more parts. In the energy segment, they need to make big parts often. So this is something that we see as more long-term. I was talking with Johannes before about the fact that in this forecast, we did use a coefficient to try to forecast the impact of COVID on ceramics additive manufacturing. So we do expect that overall the segment is going to be somewhat affected in this year and the next. But I was talking with Johannes about the fact that they were not heavily affected, and we think the reason for that is obviously that high-end applications, so advanced ceramics, are less affected, and the highest end technologies are even less affected because it's more. It's more of a high-end segment that does not have the same kind of mass demand requirements that are affected by the COVID.
David, excuse me a little bit. So I am relatively new in your system as with your product. Could you send me information about some application in electro industry or automotive industry and so on?
Yes.
So basically,
absolutely, Daniel.
In the plastic industry, and I think that perhaps you can use your product in the tools. It seems not so easy. Also, could you send me just for idea?
Absolutely. Just one thing. I don't know if we probably didn't say this before because I wasn't present. But you can write all the questions in the chat system, and we will have a session for Q&A at the end of the presentation.
Okay.
And
thank you.
We will answer all the questions that come in.
Okay.
So we will answer all the questions that come in at the end of the presentation. And with that, I'd like to pass the controls over to Johannes to look at what the actual applications are in the semiconductor manufacturing segment. Once again, I apologize for the incident in the beginning.
So thank you very much, Davide, for the introduction and for giving us some insight into the market. I think this is very helpful for the audience to understand, and definitely I will also give some kind of application to see where additive manufacturing can be used. First of all, let me just introduce you a little bit to Lithoz. We are the world market leader in additive manufacturing of high-performance ceramics. Here you see our team last autumn. So we are about 70 people here in Austria, and also we have a subsidiary in the United States. And we are a solution provider. So we are offering the printers, the materials, software, and also customized solutions. And of course, we support our customers and partners as well in the development of ceramic applications in additive manufacturing. Currently, we have 70 or say nearly 80 machines worldwide already, from Australia to China, Singapore, Europe, of course, United States, Latin America, so all over the world. And what I think is very important for us, and this is where we see ourselves as well, is that we don't see ourselves as a supplier, but as a partner. And here we can see that 25% of our customers have more than one machine, which means once somebody is starting to work with this technology, we can make him successful and applying this technology in his industry. It's a way to go, but it's possible, and we see that that it makes sense to have a very honest and down-to-earth approach and show, on the one hand, the potential, but also the way of additive manufacturing in the ceramic industry. Here you see some of our customers. 2/3 of our machine are based in industry. Most of them don't want to be public, but for those who are already in ceramics, they for sure know Morgan or Bosch, which is working on the Cerix, as well as other companies all about Steinbach Alumina Systems all over the world. And also for those who have not such a good knowledge in ceramics, so for example, the Fraunhofer IKTS, I would say the leading institute in ceramic processing technologies worldwide, is based in Germany, in Dresden. They have already 3 of our machines up and running. And this shows that I think we are really making something very important here. And we have all over the world also research institutions working with our technology. So ceramic materials, let's start with that. For those who are not so familiar yet with ceramic materials, I would like to give you a basic overview of what we are talking about and why is ceramic used. So basically, maybe ceramics from your teacup and from a coffee cup. This is also ceramics. This is not high performance ceramics because it breaks down. It breaks when it falls down. But high performance ceramics have a different application. They are, for example, they have a very high hardness, a very high abrasion resistance. So this is sometimes used for tribological application, but also a very, very good heat resistance. They can be used up to more than 2000 degrees Celsius. You see on the picture how you can heat up those things. I'll have a video afterwards as well to show. And they also have a very, very high mechanical and dimensional stability, even at higher temperatures. So the mechanical strength will not go down with higher temperatures. And it also has a good corrosion and oxidation resistance. So it can be used also in very corrosive environments. And it also has an electrical and thermal insulating effect. So basically, to sum up what's standing here, is ceramics are used in harsh environments, which means high performance ceramics are used where other materials fail. Also, one area of application is biomedical engineering. Why is it used there? On the one hand, or ceramics can be bio-inert, so they don't show any reaction with the body. Also, of course, no allergenic reaction, but also no other reaction. Or they can even be bioresorbable, so that they can be used as a bone replacement material and can be absorbed by the human body and replaced by natural bone. Also, here the advantage of the low thermal conductivity is seen, because what I learned in the past is that people with metal skull implants, they feel the heat, so they cannot go into direct sunlight, they cannot take hot showers, because this is pain for them. And here we have the ceramic materials which does not have such a high thermal conductivity. Also, it does not show any artifacts in computer tomography or magnetic resonance imaging, CT or MRI. Of course, since you can use it at very high temperature, it's also easy to sterilize the material, and it can also bear a lot of high mechanical strength, and it has a good wear resistance, which is maybe used for hip cups and stuff like this. So you see, ceramic is actually a broad range of application, and it's always, as I said, ceramics are used where the other materials fail, and so to say, they have a superior material properties. But of course, it's a special material, and it needs to be also taken special care during processing. But you will see how later on where you can always use ceramics. So here you see some of the ceramics material which we are providing. Our range of material is growing. Here on the on your right hand side, you can see the typically ceramic materials like alumina, zirconia, porcelain. Even we even have done something porcelain. In the middle, you see those bioresorbable ceramics, tricalcium phosphate, hydroxyapatite, bioglass, but also non-oxide materials like silicon nitride, and also, which will come later on a little bit, the silica-based materials for casting cores, also refractory materials, magnesia, cordierite, but also regolite, which is moon dust. So we also, for the European Space Agency, we were also printing moon dust. And I saw already a question from Mike about the PCT ceramics, so ceramics which can be used for electrical applications with a high dielectric constant and a low loss tangent. With Mike, we will definitely provide you with more information. I have not focused today on this one, but we are already working here as well with ESA and other companies on these radio frequency components, which is actually a very interesting topic. But you see, I mean, this is really a broad range of material. Basically, we can use every ceramic material to be processed. It needs some time for development, of course, but so far we have not seen that we see any huge problems with any ceramic material. Our strategy is to adapt the technology to the material, because for the ceramic engineers, it already makes a difference which kind of powders they're using. So in contrast to what is seen on the metal side, where you see that the the metal powder has to have certain specifications, we are trying to use the material as is and adapt the technology according to the needs of the powders. So what can we reach, or what is the material properties we are reaching? Since we don't have too many ceramic engineers or too many experts here, I don't want to go into detail here, but just I think the most important message, what you have to take away home message, is we are achieving the same material properties as in conventional forming technology. So we are having densities well below 99%. We had the 4-point bending strength or the strength. These are the most two important issues, density and strength. They are the same as in conventional forming technology. And something which we are very proud of as well is just by using the printing itself, we can reach very, very low surface roughnesses or very, very good surface roughnesses. So we are well below 1 micron of RA value. You can check them out on our website. We have all those data on the website, but to show you that we are really are comparable and have the same material properties as in conventional forming techniques, you see here silicon nitride, one of the most difficult materials in ceramic processing. And what you can see here actually is that there is no difference. As well in the density, in the strength, in the hardness, it's all the same. Yeah? If you have any question here, we can answer them at the end, but I don't want to go too much into detail of the material properties, as again, take-home message is we can achieve the same material properties as in conventional forming technologies. How can we achieve this? So what is our technology? How does the technology work? Our technology is named LCM-technology, which stands for lithography-based ceramic manufacturing, which means we are using light as a structuring method, but I will come to that in a second. Here you see the process chain. Of course, we have to start with the CAD data, and then we have to 3D print. But then this is not yet finished because we are printing a, so to say, composite and have to debind and sinter afterwards. I will go into this into more detail just in a few slides. But this is an important message for you. This is a two-stage process, but on the other hand, this is the normal way how ceramic are processed. So it's very there is basically no ceramic forming technology conventionally which doesn't have this two-step approach. And then we have the final product. But how is the technology working? First of all, we are using mask exposure. This is very important in terms of productivity because we are exposing the light or the layer in one go and then building it up layer after layer. I'll show you here the video how it works. You can see now the movement, it moves down. It exposes everything in once, a couple of seconds, moving up again. Then we have the recoating. We are recoating the layer, moving down again, exposing with blue light and finished. So this is actually how layer is built upon layer. There are also some YouTube videos available to go here into more details. But what you have to bear in mind is here, we have a mask exposure and we are building it upside down. So we are pulling the part out of the slurry, which has actually very good advantages because you are using very, very little material. Even for mass production, you can really save a lot of inventory and have a very efficient and effective process. So after we have printed we have, as I said, the so-called composite. So we have here the ceramic particles and the binder, which holds the particle together. So then simply we just burn off the binder and we are left with the ceramic particles. And then we have to compact them. And this compaction, so to pull these particles together, is called sintering. And by having this sintering, there is a shrinkage of the material or of the part. And here you can see how a CEO can shrink during his work, getting always a little bit smaller. But here, this is the so-called green part, the white part where it's already debinded, and then the sintering where we achieved and really full density and this stage we have then the ceramic properties. So this, as I said in the beginning of this is a normal ceramic processing step. And as well here, I think there is no fear of having this shrinkage. This is just a value which is anyway automatically added by the software, and it is compensated for that. And that's simply what you have to bear in mind here. Here you see our range of systems. So we have the Serafab 7500, also in a dental version, and then the more industrial versions, the Serafab systems with different resolutions, different building envelopes. I don't want to go into details here, but I think here is our key message is here. Our approach, and this is what we learned from the metal additive manufacturing industry, and in additive manufacturing, it's better to stack small machines together than or to have one big machine, because you keep your flexibility, you keep the advantages of additive manufacturing if you're staying with smaller machines. Also, what's on the way, and we will present it quite soon, but here you get a sneak preview in our multi-material machine. So Serafab 2M30. Here we are working with two vats, and we can do two different materials at once within the layer at different layers. So here you see some examples what we have already done so far. This looks very, very promising. We even could combine different material, different colors, whatever, or even we will also work on combining metals and ceramic. This is also well known from LTCC or HTTC. So this is something we are currently looking into it, and very, very promising to see here some very good results. You will see much more in the future here about multi-material as well. So, and now coming to industries and application, solution and success stories. So where are these technology really used, and where are the parts really used? So on a general level, we have three different business units. So on the one hand, we have the industry, where you have machinery components, electronics, but also semiconductors, and as well luxury, like watch houses and stuff like this. Then the next important thing is for us medical. There we have dental applications, but also resorbable, non-resorbable implants, as I was already pointing out a little bit, and also medical devices. So this is our medical field. And in aerospace, I will go into detail with the casting cores a little bit later, and also space and defense. And also what we did a lot is propulsion, again, for satellites, some propulsion systems where they have to work in the space. But let me show you now some of the examples what is possible here. First of all, where you would not imagine to have ceramics, but this is already one growing field, is cutting tools. So because you can even work at even more harsher conditions. So either silicon nitride is used for cutting, or zirconia toughened alumina is used for that. Here you see some of those cutting tools also for machining here, and that this is really working. And you can see here on this video that they're really machining with a 3D printed cutting tool. You can see the sparks are flying, and here also that it's really glowing in red. So really, this is doing very well. This was the first printed tool which we used, and it was already working. And you see, always people are highly interested to see things moving and sparks around. So this is one application of area where it can be used. Another one is an impeller for heat resistance. For example, here we see some application because the temperature for the burn off has to be increased all the time, and here you can see an impeller which is really glowing red and be really with a gas burner brought to temperature very fast, and you can see that there are no cracks or anything which happens here. We also have a video on YouTube where you can see that this material, silicon nitride, is also shock resistant. So you can heat it up to 800 degrees C and drop it into water, and it will take no harm. So this is really an astonishing material. And of course, I mean, not all ceramics are like this, but this is always the thing, to find the correct material for the correct application. So this was more a little bit from the industrial side. There are, as I said, also we can think of machine components and all this as well. But also from the very interesting field of application is the medical and dental field. So we have already installed a couple of systems in Europe, North and South America for medical applications, and where our customers have already certified their processes or our technology within their processes. Here we have one of the customers of us, they have already class 3 certification, so which means that it's really the highest class of biomedical implants. And in the US, definitely there's also FDA approval. The customer there is just going for 2A, but should be also possible to achieve their medical class 3. Much more important, this where you get as a CEO and for somebody who has developed technology a little bit more nervous is when this is really going into patients. And this was back in 2017, where there were already 10 surgeries performed on humans. And this is where I say, this is really a special moment. And up to our knowledge, all these patients which have been done, and there are much more now. I don't know how many surgeries have been performed so far. But these are these bone replacement materials. And so they're really implanted into the body. It's not just a tooth or something. It's really in the bone. And all the patients which have received implants made with our technology are still doing well and still alive. So this is very important. And we see that this is a very interesting area because patients are asking more and more for metal-free solutions. What is the reason behind that? I don't have a scientific explanation, but at least if you think in nature, metals are not existing as metals. Like if you take iron or steel, this is existing in nature as an ore. So, and an ore is a ceramic material. So it's a metal oxide. This is the definition of ceramics. And so I think it's the human body it's easier for him to accept natural material like ceramics because they are existing in nature. Only, of course, precious metals are existing as a precious metal. But this might be, it's not scientific, but at least this is an idea why ceramics are more suited for biomedical applications. Here you see some examples. A jaw implant. Here we have tried to make a showcase to combine the best of two worlds. So we have on the one hand this cage, the outer cage here. This is made of zirconia, a load-bearing material, and the inner one is a mixture of TCP and hydroxyapatite, which is then biodegradable. So the bone can go really eat himself or resorb the material inside and grow through that and really replace the blue part here with natural bone or with its own bone. But also I mentioned dental is an important topic for us. What we see here is there are applications beyond machining. What we think is one of the applications we're looking at is ultra-thin veneers, or as you call them, non-prep veneers. So veneers which are put on the teeth without making any machining or any grinding of the teeth. And also, this is really interesting, are dental implants, either made of zirconia or even of silicon nitride, which shows some very, very good antibacterial properties. But there will be a whole webinar dedicated to dental implants only. I will show you in a second. And of course, you can also make bridges and crowns and all of that, what's possible in the dental field. Also, a very, very good application of ceramic materials. What I have to admit that I didn't know about this application 10 years ago when we started the company. So the turbines for aerospace, but also for industrial gas turbines, so for those for energy generation, they are in a range of where it's very hot, and they are even in a range where the material should already melt. So the metal material should already melt, but it has a very highly sophisticated cooling channel system and also other things like thermal barrier coatings to bear this high temperature. And they have to be casted. So these are single crystal materials and they are casted. And you need then, of course, if you cast something, you need to retain the holes. And therefore you use silica-based materials. So this is typically this casting core material, and this is leached out afterwards. And here, the cool thing here is that the engineers or the companies already know that the new design, which comes up in 10, 15 years, cannot be injection molded anymore. Usually these cores are injection molded. So we see here a strong application for additive manufacturing because the new designs, which can even increase the cooling efficiency and hence the efficiency of the engine and the fuel efficiency, will even enhance it, and it will be even much better. And this is where we see where additive manufacturing could really be very, very beneficial. But of course, it can also be used for small scale series and for prototyping. And here we have already, this is cool, we've already done our first single crystal casting successfully. So this is a big step, and you can see that it's really in use. Something beside the moon dust, which we already have printed, the Colorado School of Mine printed also a part of the Ironman suit. So this was a project from Andy Savage. You know him maybe from Mythbusters. He wanted really to 3D print this the Ironman suitcase, or the Ironman suit, sorry. And of course, he was using metal for the outer shell, for everything. As you can see here, this is all done in metal. But the most important part of the Ironman suit, of the Ironman itself, is the arc reactor. And this was printed in ceramics. So you see again here, ceramics are used where the other materials fail. And this shows, it's sometimes ceramics really makes a difference between living and not living, but it's always or sometimes very good hide it, and the other materials are taking more space, but it's a very important material. There's also a nice video about then when they were really flying this suit that looks really cool. So here I'll already come up to the end to leave about 15 minutes or even more if you like for question and answers. But just to sum up here, I think what take-home message are that ceramics are used where other materials fail, and there are a lot of applications for this kind of materials. And the 3D printing process is already available for different ceramics and can be used basically for every ceramic. And I think what has to be mentioned here as well is that we are already in production, and this is what I showed you with this video where they are really used in the cutting tool or really used in a gas burner. This is not prototyping. We cannot. It has really to fulfill all the requirements as the standard material. So I prefer when we talk about ceramics. And additive manufacturing of ceramics is we cannot do prototyping, but we have to do production with a lot size of 1. And this is the key message. And we are already in serial production projects or our customers are already in serial production projects with 5,000 to 10,000 parts per year. So it's not on the edge of coming. Ceramic additive manufacturing is already here. And I think what I've said in the beginning with this, that 25% of our customers have already more than one machine. This shows our willingness to show or to be a partner. And so we as Lithoz, we can support you with our know-how and experience and really starting from the CAD data to the final part, to the application. We can guide you here through that. We can support you. And as well, our customers can do that. So it's not only us who can support you. There are already a couple of customers out there. Feel free to reach out to us if you have any questions. And I'd also, if you are now more interested in ceramic materials, I also want to show two other webinars which are coming up in August. One is basically in the US. It's at 5 p.m. Our time. It's a webinar together with the Sandia National Lab, and it will talk about pioneering through cooperation in ceramics additive manufacturing, to show how important collaboration is here and how easy it is then actually to achieve your goals. And as I already was pointing out, there is also a dedicated webinar to ceramic dental applications, especially to implants. This will be hosted by our Daniel Bomse, and together with Dr. Taj from the European Ceramic Implant Society. So this is also very highlighted. And if you even want to dive deeper, there is an event which is now in its 4th year. It's the AM Ceramics, together with the Ceramic Tech Conference. This was supposed to be a physical event in Dresden, but due to the travel restriction and due to the Corona crisis, we decided to move it into the virtual room, which has for you the advantage that it's now a free to attend webinar. Unfortunately, it has been a little bit shortened, but anyway, it's a 2-day event. One day focusing on ceramic applications in general, and the other day on additive manufacturing of ceramics. So, last but not least, let me thank you for your patience, for your audience. I hope I could give you a little bit of insight into ceramic additive manufacturing. I'm happy to answer all the questions you have. If some or more questions are coming up, please feel free to get in contact with us via email or website. There's also plenty of information on our website to read, also on our YouTube channel. Whatever you find, feel free to look into that. And thank you very much for attending the webinar. And now, Davide, I'll turn back to you to moderate the Q&A session.
Thank you. Thank you very much. Hopefully we will not have additional thunderstorms. The sun is shining right now, so we should be okay. We have a lot of questions, and thank you very much for that presentation. That was great, and it's great to see how far you've come in this year. So let me start with the first questions, because we have a lot. Hopefully we'll get to all of them, and some of them are very specific. So the first question is, what about BAM? I'm guessing aluminum magnesium boride composites. Is that a material that you are considering?
Say it again.
BAM. It should be. It's like aluminum magnesium boride. Composite material.
BAM.
It's like ALMG B14.
I'll check out the
very specific question.
Yeah, but basically, I mean, I've not seen which exactly material it was, but basically, as I said, we can really do basically every material, and if we cannot do it, we cannot adapt the technology. So we are really working on the given powder. So far, we have had a lot of materials, and I don't see a reason why it should not work. It might be more or less effort to develop it, but basically it should be possible.
Another question.
I just see that I have here a private question: is can you also have silicon carbide? Yeah. So basically, I just
that's a good question.
One of the yes, we have already done silicon carbide. We have done recrystallized silicon carbide. We have done SEC. And we are working now on a process also to make SSIC, so the sintered silicon carbide. This is already on the edge. It's not yet ready for marketing this material. We have the let's say Austrian-German engineering tradition, so everything has to work 100% before we go public. But if somebody is interested in silicon nitride, there are sure some possibilities to work to get something started.
Another question is broader. I think you addressed this during the presentation. Is what about the post printing processing? Like what does that involve?
Yeah, the post printing. Yeah, basically, you take off the material from the building platform, which you usually do by with a knife. Then you have to clean it a little bit from the excess slurry, which you do basically with an airbrush system, very, very simple. And then you have to debind and sinter it. And debinding means you're burning off the binder, and then sintering means the densification to really get the ceramic part. And then, you can also finish it like you can afterwards machine it, polish it, grind it, whatever you can do to ceramic materials.
Fantastic. And another question that is quite specific is if it's possible to create ceramic gears for high-speed electrical tools in place of, I don't know how it's pronounced in English, but it should be bakelite. Bakelite.
Bakelite. Okay. Bakelite is definitely a material which should be possible to process, and yeah, I mean, if I'm not sure if I understood it correctly, if the ceramic materials are already used, if this bakelite material is already used there, but basically, if the application really is, let's say, in hot environments or stuff like this, it really makes sense to think about ceramics, definitely. I don't know if bakelite is the right ceramics to be used, but this would be something we can discuss also with the Fraunhofer IKTS or with other experts to get the right material.
Fantastic. And another question that's more on process is what are you doing to address the needs for serial production, mass customization / mass customization?
This is a hot topic. It's difficult to go here into details, but what I can just say is that we can definitely we are ready for serial production, and our customers are already doing this. And this starts from quality control from material quality control over quality control of the machine, of a reproducibility within the machine and within different machines, within different jobs, within different machines. So this is something which you really have to focus on. And we could show that we can have, we achieving reproducibilities around 10 microns. We have even customers who achieved a reproducibility about 2 to 3 microns. And this is really astonishing. And I think from an additive manufacturing point of view, this is really something very unique. And yeah,
I have to say that I think when you see the parts that you can make in person, they're really, really are impressive. There's really no words to describe, I think, how nice they look.
It's on the one hand the parts, but on the other hand, all these, so serial production, there's for sure a difference between prototyping and serial production. And this is this was what I'm trying to say. Here we are trying to establish ourselves as a partner, and we have been successful by doing this because 25% of our customers have more than one machine, so they are already producing more than that. And I think this is really something which is coming up. It's really going into this direction. We already see that some of the project which has formerly been injection molded with comparably low quantities, 5 to 10,000 parts per year, that they are moving now 100% to additive. And this is, and time by time, we will increase this number where it makes sense to move into additive manufacturing. And then the switch between just moving from a technology to the other is then, and this is, Davide, you know that this is a very important topic, to do also design for additive manufacturing. This is really the key in achieving the goals. This is, if you really have a part which you can design for additive manufacturing, you are really making use of the full potential of additive.
And also, I think one of the reasons in our forecast we saw such a rapid adoption once the technology matures is because the materials are such end-use, they're perfect for end-use applications, and additive could give more opportunities to process these materials into complex geometries, which are not possible otherwise. So that's kind of one of the reasons that drives up our forecast. So back to the questions. I have so there's another question. If you could provide some more information on piezo ceramic.
Yeah, definitely.
Material.
Yeah, piezo ceramic is also something which we are working on. There is even a publication from Lithoz America on LinkedIn, on Twitter. You can follow up us there as well, showing that we were already able to do some transducers. This is definitely very, very interesting material, also in combination with metal. This is really, I think, also one of the promising materials to enable much more in this industry. And we have done LED piezos and also non-LED piezos, so non-LED containing piezos. So PCT.
So sorry to interrupt you. I wanted to warn you that we have a lot of questions. So
okay. I'll try to keep myself short a little bit. Yeah.
No, and I'm sure we can follow up directly with more. But we have there's really a lot of great questions here. So these two questions are quicker, probably. So what is the shrinkage in post processing on the XYZ axis, and what is the maximum part size you are capable of?
Yeah, the shrinkage is usually this is dependent on the material you use, but basically it's only a matter of the filling ratio and defining the final density, and this is typically in the range of 20%. So this is the typical shrinkage rate, but it's homogeneous and reproducible. So this is not something you need to worry about it, because this is automatically compensated by the software. And the biggest part size, the current machine which we have is 120 by 192 by 500. So you could see, just a second. So
this is really, I would say,
this core here on the right-hand side, this is 500 millimeters, so half a millimeter in size. But for even bigger parts, our notion is that we don't think that lithography-based technologies like stereolithography, they are not made for big parts. It's better to. We are working on a different technology which will be able to make big parts with thick wall thicknesses. We'll come up early next year with that.
Thank you. Okay. Can you give an idea of the rough price of the machine? In this case, in this particular question, they want to know about importing to India machine and material.
Yeah, the machine starts roughly about 240,000 euros, and can go up to 400 or so, depending really on what is needed.
Very good. Another question on materials. Are you printing with Cylon or silicon nitride with sintering aids?
Yeah,
which I'm not sure what sintering aids are. I'm repeating.
This is but basically silicon nitride with sintering aids is a Cylon. So this is academic discussion whether it's silane or silicon nitride, but basically nearly every silicon nitride is actually a silane. So you need sintering aids in order to support the sintering of silicon nitride. Yeah.
Okay. So this question is about this user is asking for to receive information on the application of ceramic materials. So I think mostly they want to understand what the key applications are in machinery, electro-automotive, and medical applications. I think we can probably provide these.
Yeah, I mean the key. We see there is really nothing where I say this is the best ever. It's really that we see a lot of areas where additive manufacturing can really give added value. Definitely, it's.
Another question was, why was the piezo ceramic material shown red?
Because that's the material as it was used. This is I think it's a barium titanate.
Okay.
And it's just
great.
That's how it is. Yeah.
Great. No, and that was the next question. What material was it? So, and back to part size. How thin can the walls be?
Yeah, that's actually a good question. This is actually what we're working quite a lot of it. So we were really able to make a complex structure, like something you see like here in this, with strut thicknesses below 100 microns. So really thinner, and Davide, we both can talk about hairs. We know this, yeah. below the thickness of a human hair, that you really have a structure which is well below half of the human hair. Even we could go down to 80 microns in strut thicknesses. So this is really, I think, this is really unique, and this really takes. It is really a challenge, but we mastered it.
And then I have another question, which is asking, what is the maximum wall thickness? And I think they actually mean the wall. How big?
I mean, the thing is that and this was why I was talking about this other technology. We have a rather high binder content, and it takes time to burn off this binder. And when you do this too fast, the part gets cracks. And the thicker the part, the more difficult it is to debind. We see currently a limitation about 10 millimeters wall thickness. This is, so to say, over the thumb. If you have parts well above 10 millimeters, this is getting then difficult. But basically, below, usually, if you really design for additive manufacturing, you can get rid of a lot of material and save a lot of material. And then you can also decrease the wall thickness. But usually the wall thickness is sometimes there because you cannot remove the material somewhere. And actually everybody wants to use less material. So I think this here actually is the limitation we have on the wall thickness is actually, it drives people into design for additive manufacturing and reduce material.
Absolutely. Can you print colored materials for dental? And what is the resolution?
Yeah, definitely we can print as well colored materials, as you have seen in the slide. So we have also done dental colored material. This is it's not yet one of our main aims to go there. We have tried it, it's working out. If somebody's interested, we can go there. The resolution is actually the same as all the parts which I've shown. They are not polished or grinded. This is the resolution you see. As I said, it's well below 1 micron in RA value.
Another thing that we also saw in the presentation, but maybe you want to expand a little bit. Can you print using different ceramic in one part during the same build process?
Yeah, with our multi-material machine.
Yeah. Okay.
This is what we developed it for. So just going back.
Fantastic.
Here, you see that we can color it and that we can use different materials in here.
Great. And so when did you sell the first machine?
We founded Lithoz in 2011. By this, we already had some experience from the Vienna University of Technology, and we were able to sell our first machine in 2012. And this machine is still up and running. And even our first prototype, which we built in 2011, is still up and running. And this is what makes us very proud, because we are focusing very, very much on quality. So our goal is quality and technological leadership.
It's amazing how much has happened in the additive manufacturing industry since 2011. Okay. Are you, and you also answered this, I don't know if you want to add something to this. Are you exploring other production processes after beyond LCM?
Yes, we are working on other production technologies as well. I don't want to give too much detail at this very moment, because we are still in patent issues to file the patents and everything. But we are definitely working on it, because we don't think that one technology fits all purposes.
That's part of my forecast too, by the way, that stereolithography companies would also be introducing other technologies. I just had a feeling, so I guess I was correct. So, what are there any anticipated uses for whisker reinforced ceramics with SiC plus?
The problem with whiskers, the problems with whiskers here is that you have to spread them somehow. We have already worked with short fibers, and this was working. But the long whiskers, of course, I mean, this is, as a matter of fact, difficult to handle in this kind of 3D printing process. But definitely, it's possible.
So whisker, this is my question to you. So whiskers is kind of like the fibers.
A fiber, yeah, a ceramic fiber.
It's kind of like a ceramic fiber.
Yeah, you can also have the ceramic materials as a fiber material. This is possible. Oh, I think some thunderstorm came up again. Davide?
Hello?
Yeah?
Can you hear me again?
Yeah, we can hear you.
Okay. Parts suffer from residual stress and sometimes contaminate from the building base plate.
Okay, now we have lost him, but I'm following up on this here as well. So I think that's the main difference between the ceramic, the two-stage approach and the metal approach, and this is why laser melting is not working for ceramics. With the laser melting, you are building up a lot of stresses in the material, and with metals you can anneal it. So you put it in the furnace, you anneal the stresses, and then you have a normal structure again. But this is not possible with ceramics. It has the diffusion coefficient is far too high, and therefore it's not possible. But this is exactly why we use this two-stage approach. And we have, even compared to other ceramic traditional forming processes, we don't see any stresses, because the only force we are using is light. And so if with dry pressing, usually you have forces, or with injection molding you have forces, and this is what we don't have. And this gives us really an advantage for to other technologies. I don't know if Davide seems to be has some issues, but I'll just follow up on his questions, or Isabel can take over. There is a question like, I wish to know the sintering time required for a cubical component of 10 cubic centimeters. Basically, sintering takes a couple of hours to a day. So it's not really dependent on how big the part is, but how much you put into the furnace. But this is not really an issue. The more critical time is the debinding time. I think I need to speed up a little bit. Luxury components, yeah, definitely more about luxury. There's really a lot of things going on there. Tungsten carbide, it's a private question I received. Tungsten carbide, very interesting material. Please feel free to reach out to us. This is a not so easy question to answer right here. There was also a private question into liter core material. Yes, you can print our technology to make cores, and the size is, as I said, up to 500 millimeters. Davide, you are back again?
I'm back.
Okay.
Sorry.
Yeah, I'm now in the tungsten carbide, now at 4:49 p.m. How critical is the temperature uniformity during deep binding in the sintering process and quality of the part? Yeah, temperature uniformity is definitely an important issue.
Oh, okay.
And but usually we just use standard furnaces. So all the standard furnaces can not every standard furnace, but let's say most of the furnaces can or their uniformity is okay.
Okay, I'm also there, but that's the last question I see on temperature uniformity.
Yeah. Okay. No, I see some more questions.
Okay. Unfortunately, I think because the connection dropped,
Okay. Then I will. When do you estimate the first dual printer to be available? That was the next question. I have to admit that we have already sold 2 systems without doing any marketing here. There's again our Austrian-German attitude in engineering, that we don't show anything until it's working. But when the customer comes here and sees it, he says, "I want to have it." So we have already shipped 2 machines, and so it's already available. We'll come up with the marketing material later this year. But if you're interested, feel free to reach out to us. Davide, you are back on track, or?
I am, but I don't. Unfortunately, I don't have access to the questions.
Okay. Okay, then I'll go to the next question. Is the ceramic filler increasing shrinkage rate? What is the shrinkage rate after sintering? Yeah, the more filler you can get in, the lesser is the shrinkage rate. As I said, typically it's around 20%. To print non-conductive, is it possible to print non-conductive and conductive material in the same part? Yes, definitely. With the multi-material, this is definitely B.
Okay.
How creative can you be with structures? That's with any other additive manufacturing process. You have a huge design freedom, but you should not have a design ignorance. So you have much more freedom as with conventional forming, but you need to keep with some design rules. We can definitely support you there.
I'm seeing the new questions coming in. There's one on if it's possible to combine ceramics and resins and leather particles or powders to make composite materials for 3D printing of leather composite products.
Yeah, you can do leather. You could use basically, but the problem is you need to sinter it, and sintering is usually about above 1,000 degrees, and this is typically too high for non-ceramic materials to withstand it. So basically, you burn off everything then. So therefore, it's difficult unless you just want to use ceramic as a filler.
Well, I also have a question for you. Which is the key market for you for Lithoz, and which do you think is going to be the biggest region in adopting ceramic additive manufacturing?
Mm-hmm. Region-wise, I think it's as the, let's say, the normal ceramic market is distributed. So we see 1/3 in Europe, 1/3 in the United States, and 1/3 in Asia, meaning China and Japan. So these are the main. I mean, just as a simplification, but these are the two main factors. And the other question was.
I have another question on what are the total investments you have raised up to date.
Yeah, so far actually we have built up the company just on our on blood, sweats, and tears, I would say. So there is no investment in Lithoz.
Okay. Do you use supporting material for particularly complex parts?
Yes, you need support materials if you have overhangs, but you can remove them afterwards with a knife. So this is not really complicated. But usually, again, if you design for additive manufacturing, you would avoid supporting structures.
Okay. Does the Lithoz Serafab system support zirconia with 8% yttria?
Yeah, definitely. We've already worked on that for a customer. Yes.
For solid oxide fuel cell applications.
Yeah. SOCs. Yeah.
Could you share information regarding annual revenues at Lithoz?
Not really. We are, let's say, we are really happy at this moment with our revenue. But we have seen that maybe especially during this COVID crisis or after this now, we see a really uptake in additive manufacturing. I think that digital manufacturing or that industries are now realizing that the supply chain is not as stable as they thought, and that they are moving into digital production technologies. And I guess it will be a good year for us again.
Fantastic. And this is another question you actually referred to before. Does Lithoz have any plans for introduction of continuous fiber reinforcement to ceramics using additive manufacturing?
Not now. No, we don't have any ideas in this regard. This is difficult to do with the LCM technology, but happy to discuss this in more detail with the person. Yes.
Fantastic. And so there was I think this maybe was a reply to an earlier question. And it refers to the fact that the binding and sintering process can create stress.
Yeah.
How important is temperature uniformity?
Yeah, I think I answered this already. So it's important, but nothing special in terms of furnaces.
Okay. And another one is how creative can you get with structures?
I answered this question already.
Okay. Very good. Okay. I actually don't have any more.
I think we've already 20 minutes overtime.
Yes, I think so. Exactly. Sorry about the complications with the connection, but I think it was quite an interesting, a very, very interesting presentation. Lots of topics to discuss, and I'm sure we'll have an opportunity to follow up.
Yeah. If anybody has additional questions, please feel free to reach out to us. Happy to discuss them.
Thank you very much to everyone for participating, and we will see you with the next events coming up.
Thank you as well. Thank you, Davide, for the good supporting, and all the best for everybody. And hope to see you soon.
Take
care. Bye bye.
Bye bye.